Okay, yeah. So yeah, my name's Clint Seinen. I do a lot of the technical work at the CCCMA. I've also been working quite closely with Neil Swart on this project, and also just the whole Candy development team. It's quite long, so I won't include on the names here, but there's all the references back to all the papers. Everyone is intimately involved in all this, ranging from our domain scientists to our technical staff. And so, yeah, I'm going to be kind of just touching on, some people might consider this the boring bits of this type of stuff, but it's very important just for running these models to understand kind of the high level aspects of it. It should probably be shorter than the other talks, but so a bit of break there. But yeah, so we're going to be touching a bit on the repository and some version control stuff, but we'll be touching on more details on this stuff tomorrow. And then just some important systems and concepts that when you run this model, just ideas to keep in mind. And then we'll talk about setting up the setup flow and the simulation flow. Now, I want to just have a disclaimer out here. Is there are currently two different CAN-ESM modeling systems. There's one that we use internal on the ECCC computers, which is where our bleeding edge development goes. And this is where we're kind of doing this prep for CAN-ESM 6. And then there's external CP4C that we have set up to run on Niagara, specifically from the DRAC machines. And these are stable versions for these external applications. We are doing work to consolidate them, but until we have them fully consolidated in the same systems, there is a bit of work required. So there is that lag. There will always be a lag from our bleeding edge version, but right now it's a little increased. And then, so I'm just going to move on from that and just discuss. Neil briefly mentioned this, but on the slide, which will be shared, it has the links to our GitLab.com, our public GitLab, CCCMA CAN-ESM. And this is, as Neil mentioned, this is mirrored from an internal GitLab repository that only CCC scientists will have access to. Now, CAN-ESM is a super repo. I won't get into huge details, but essentially what that means is there are individual repositories underneath. Now, if anyone has worked with submodules or subtrees, it's a little bit of a mess, but subtrees and submodules is just kind of necessary for this application. So CAN-ESM is a super repo that contains a bunch of these subrepos, and I'll just kind of briefly touch on what they are. So CAN-AM, you've heard this from Jason Cole. This is where all the version control exists for the CAN-AM, the Canadian Earth System, Canadian Atmosphere model. You have CAN-NEMO. This contains all the stuff that Jim was just talking about. And it also has some of it supporting scripting and supporting programs in there. CAN-COUPLE is the source code for the coupler, which is what executes the boundary conditions between the ocean and the atmosphere. CAN-DIAG is full of diagnostic scripting programs for CAN-AM, but also a bunch of CAN-ESM general scripting. And CCMA Tools is kind of this higher level support software that we need to run all this stuff. Notably, this is where a makefile generator source code lives, or MakeMuff, as Paul is credited with the terminology for, or MakeMF. And then on the output analyzer, Seamerizer, and our file management systems. So one of the big things that you'll see when you run this model is you'll run into kind of these scripts known as access and save. People refer to these run databases all the time. Now you can get into the technical details of this, but essentially why we use this is this model requires a very large amount of input files, and the model also produces an extremely large amount of files itself. And then the post-processing also creates many of these intermediate files. And so we use a file management system that relies on disk SQLite databases at the moment, and these helper utilities like access and save are the most visible to users. And basically this just lets us have scripting that just says access the file name, access it with this local file name, find the stored file name, and it's going to go into the databases, find the stored file name, and it's going to pull it in. And so we don't actually need to have explicit knowledge of where these files are stored within all the scripting, within all the scripts. And also it gives us the ability to share files. And as you'll see, if you work within the CP4C space, there is a global database which we use to serve up all the forcing files. And it also lets us do some versioning for the file specifically. And then the other kind of big component that you should keep in mind is that CAN-ESM, like most of modeling systems, they rely heavily on a checkpointing system. And this means that the model will shut down, has the ability to shut down, and it will drop the entirety of the required prognostic state of the model or the field state variables that it needs to pick up again, pick up from the exact spot. And now someone might ask, why do you do this? Why not just run the whole experiment? And that's just because, yeah, climate runs are long. And even on most supercomputers, you're not able to run for more than a couple hours at a time. And so sometimes we might be running certain experiments. For instance, if we're trying to spin up a pre-industrial control, trying to do thousands of simulated years. So it's not feasible to just do this in one simulation, let alone have all the post-processing and diagnostics also run after. And it also lets us have better system crash recovery. So if some hiccup on the machine causes your model to crash, you wouldn't have to redo countless hours of simulations. You could just pick up from your last checkpoint. And that also lets us daisy chain a bunch of experiments. The pre-industrial control will create restarts that will be used in historical experiments. And then those restarts will be used in the SSP runs. So as you're working with this, you'll notice that there's actually 3 specific restart files that we refer to. We call them restart bundles. There's an AGCM restart. This is all the files that the AGCM needs to start up. It has this file suffix AGCMRS. You have ocean restart, likewise, the same thing, the ocean state variables, but with NEMO RS. And the coupler's a little different. This explicitly contains the boundary conditions from the end of the previous simulation. So it gets those and then instantly sends those to the next component, to the relative component, which lets it be able to just pick up, assuming the boundary conditions are forced properly. And then, so yeah, when you're setting up the run, this means that there's always a step where you have to save the desired restart. So some helper tools to make this easy to do. And then the codes will automatically do the save and accessing of the restarts as the model run progresses further. So as it kind of keeps going, it will automatically do this and you don't have to really worry about it after the initial save. Moving on to the next thing you'll notice as you work as part of this is, yeah, this is a compiled model and has a bunch of compiled supporting software. So yes, we need to have various build systems. And so with we have a single entry point for this that does kind of all this stuff behind the scenes for you, but you can delve into it if you'd like. But so you get a CAN-DIAG library compilation, and this helps handle kind of the CCCMA format stuff that comes out of the AGCM. And it also provides a library that gets linked into both the AGCM and the coupler. And so you can follow these links if you'd like. It uses a makefile for this. The makefiles get kind of hairy, but it is still just a makefile. So you should be able to look at it and gain some insight. And if you ever want to add programs to it, that would be where you do it. Next, you have the CANM executable. And so this, go back. So yeah, this is just the executable for the AGCM model. And this we use MKMF or MakeMuff. This is a makefile generator out of NOAA or GFDL specifically that you can bind with a makefile to dynamically figure out the dependencies of structure of these models. Likewise, CAN-couple uses the exact same system, but just has a different file list. So it scans over those files and figures out the dependencies. CAN-NEMO uses a tool chain. Build NEMO, something we built as a wrapper around build utility that shipped with NEMO, the NEMO model itself. And then this also builds kind of all the supporting programs. Now, I will use this as an opportunity to mention that the CAN-ESM model runs in what is known as a multiple program, multiple data framework, which what that means is MPMD for short, which means that the run command consists of 3 executables being launched at once. It's a little complicated, but it just allows us to have separate executables for each program. And then when they all spin up, there's a various communication at the MPI level to kind of decide how to subdivide tasks and pass information between the various executables. Now, moving on with that, I will just discuss kind of the simulation setup flow. And this applies to both of the systems that I discussed earlier. And I will be discussing this, showing a demonstration of this tomorrow when I talk about setting things up on Niagara. But essentially, every simulation follows this setup flow. You set up, and what this does is this clones the source code. And this is following an idea that all simulations should have all the source code they need in their repository. There is obviously some system level setup that needs to be done that isn't part of this, but the majority of all the code that's necessary to actually run it, provided you have the right system environment, comes out of this source code cloning step. This gets cloned down, and then it does some extra setup to create a run directory for you. Then you have to go through a configuration step. And this is where you can change these things like Jim was talking about, changing things in the name list. You can change things in the atmosphere name list. You can change things in some shell scripting parameters. And there's this configuration step that you need to do. This is kind of combined both of these steps in the DRAC system that we have, but there is still an explicit configuration that you can expand on it. And then you will build the executables for your configuration just using our build systems. You have to save the restarts from the parent run, and this is often referred to as the parent run ID. And then you just submit the simulation. And then once things are submitted, you kind of follow this basic model, model simulation flow. The submission submits the model run, a model run job. And this gets the input files, it gets the configuration files, and it runs the models, and it leaves tiled raw output on disk. And then right when it finishes, all it does is it saves the output files, and then it submits itself again. And this is just to kind of fit within the wall clock times. We typically are running on order a year or two, maybe 6 months in one simulation chunk, and then it resubmits itself, and it keeps going from there. Now, after each model run completes, though, an entire post-processing pipeline gets triggered. Now, in the internal ECCC system, these jobs are separated into separate jobs as they run through the queuing system. Currently, on the Digital Research Alliance machine, Niagara, we run these as one longer job because we have a bit of a longer wall clock we can work with, and the sequencer hasn't been as flushed out as the internal one. But essentially, the first initial phase after the nth iteration of the model run is done, the rebuild output, there will be a parallel job or two different steps for taking the AGCM tiled output and taking the ocean tiled output, and it does some rebuilding and stitches them back together to produce the global files. Then these global files, they get used by both the diagnostics and runtime diagnostics. Now, the diagnostics are kind of the basic analysis on the output data. As I mentioned here, pressure level read grids, time means, you get spectral transforms to take the AGCM fields out of spectral space. And those produce a lot of like 2D, three-dimensional diagnostics. Then the runtime diagnostics, though, as was alluded to in a couple of these other presentations, it takes the global data and then it reduces it down into 1D time series, which then gets served on that RTD browser, producing those nice plots that Jim was showing. And so these typically they run separately, these two different jobs, but just want to make it so that those things are explicit, as the RTDs are all about getting these one-dimensional reductions. And then that lets you see kind of a 1D reduction of how the climate state is progressing. It's not the end all be all. Don't just use that to diagnose your models, but it is a great place to start and monitor runs as they're ongoing. Then the diagnostics, once the diagnostics is finished, this triggers the CMARization. Now the CMARization, this is pretty important. Paul alluded to this before, and this is what produces the CMARized output. Now the CMARized output are net CDF files, a single file for each variable that fit the CMIP standards. So if any of you have done any analysis on the CMIP 6 ensembles, this data format will look the same. It will look the same as this. The metadata might just be a little different for the CP4C system, but it will be the exact same net CDF format. So your scripts that were used to analyze the ensembles should be able to pick up these files as well. And then at the end of this, there's always a cleanup step on both systems. So the cleanup step, what we'll do is this will just clean up your on-disk location of temporary files that you can change some of the stuff in the configuration to make it leave more on disk, but keep in mind, this is a large model. And even though our resolution is low, it leaves a lot of data. So you need to be aware of this. And so this is where there's on our internal system, we have an automatic archiving step, and we'll probably incorporate that into the MZ system, or sorry, the CP4C system. But this is where if you have really long-term files, send them to archive or send them to tape. But yes, there ultimately needs to be a cleanup, otherwise you'll blow out your disk space or blow out user space. So you need to be aware of this. And that is the end of this. So I will open it now up for some questions, if there are any questions on these systems. And yeah, keep in mind that we will be elaborating on this stuff more tomorrow.
I wanted to lead with again, thanks a lot, Clint. I wanted to just lead with a kind of more of a science question about this. One thing and it's again another note for the future, but we're talking about the components of CAN-ESM. We haven't really talked very much about the coupling, and I think it would be worth at some point getting into that. And I don't think we can do it today or tomorrow, but that warrants a separate discussion. But it can be very important. It can be really important. It can be important for constraining simulations, for resource use, for all sorts of, and I know that there's separate executables. I don't actually know fully the coupling framework either. So maybe that can be summarized sometime, but that's it. No,
that's a good point, Paul. Thanks. Yes, people can ask a couple, just send a question to us about the coupling of it. But yes, I do agree that would be useful to have a little more formalized information on that.
Anyway, so there were actual questions. I think I saw Christian Seiler's hand up, and then others. Like maybe it's that question.
Russell, do you want to go
ahead? Can you hear me?
Yeah, we can hear you.
Okay, great. So I noticed that you didn't mention the land model in your description of the infrastructure. So I was just curious where it lives. Is it something separate, or is it incorporated in somewhere what you described?
That's a great question, Russell. Yeah. So the land model is embedded in the atmosphere model at the moment. It gets compiled into this, and we are like it lives on the atmosphere grid as well. And we are going to be as Vivek mentioned, moving towards the classic, and that is still following in this framework of being right embedded in the atmosphere model. There's possibilities of splitting it out into its own executable, but that's a bigger question at a later point. But it is currently just embedded right within the AGCM.
Cool. Thank you.
Christian, go ahead.
Thanks, Clint. And then following on that, when do you think Classic will be available?
So Classic, so we can discuss this more because it's going to come up a fair amount. So Classic is currently being integrated into our 5.2 model, and that's even with various bells and whistles turned off, and there's still going to be kind of tuning aspect on that. So there will be, at the very earliest, I would see it when we release 5.2, but the tuning effort for 5.2 is just starting now. So that's even going to be a couple months as the 5.2 is matured internally. So I wouldn't say it's on a very quick time frame that Classic's going to be available. I would probably put it out at 6 months to a year that the Classic would be available on the CP4C systems. But it will eventually, we will eventually kick it out, but it's going to require us to do the validation of 5.2 internally. And Vivek and everyone's going to need to decide on the settings that are going to be used in our 5.2 model, and then it will be available there.
Okay, thanks.
Kimberly? We can't hear you. You're muted.
You're muted.
So sorry. Okay, can you hear me now?
Yeah.
Yes.
Yeah, okay. So I know you talked about how there's like kind of the two different versions of CAN-ESM, like there's the one on the ECCC computers and then the one on the CP4C. So I guess like, are those different? Like could I run like kind of the, develop CAN-ESM branch on the Niagara, or is that like delayed quite a bit?
Okay, so actually this is a good question. Develop CAN-ESM, we are trying to merge the whole CP4C supporting branch into Develop CAN-ESM. That should be happening in a couple weeks. So with that said, Develop CAN-ESM, because Develop CAN-ESM, I will just kind of clear this up for anyone who hasn't spoken about the internal nomenclature on this. Develop CAN-ESM is our staging area for bleeding edge work. But I need to note that there's a difference between release branches. And so there's a 5.2 release branch that is currently being developed with all like the major physics updates, but Develop CAN-ESM, as Kimberly is referencing, that is currently still at 5.1. So basically this is a long answer is yes, Kimberly, you should be able to run a version of Develop CAN-ESM on there quite shortly. But as of now, they're a little separate, but we are trying to merge those together. And it is a very similar version. The CP4C supporting branch is very similar to Develop CANISM, and that runs on Niagara.
Okay, and as changes are made, will they be pulled regularly once you get that set up?
Well, so I think we do need to discuss kind of how quickly we're going to be pushing out changes, because we need to set up as with currently the v5.1 CP4C branch, which is the recommended branch to use. That one requires us to be pushing those out. Like we have to manually decide that we're going to deploy that. Develop CANISM is currently getting synced automatically every night. So the 5.1, so we aren't automatically deploying all the changes onto the CP4C supporting branch, because we're going to have to kind of figure out all our testing regimes before we make that a bit more automated, just so we can be aware that we're not breaking anything in the same way we do with the internal merge requests and stuff like that. So we just have to kind of decide on that policy a little. But the hope is that that shouldn't be too far behind. Outside of the major release updates, like the major release updates, so like the 5.2, the 6.0, those are not going to be coming out very regularly, but the updates to Develop CANISM, which is where kind of bleeding edge technical work and little feature updates will be put onto. So hopefully that will be put out.
Okay, thanks.